Hi, I'm Eric, and for my final project, I'm going to be talking about the effect of general relativity on orbital mechanics. So first off, a little bit of history on the subject. In 1859, French mathematician and astronomer Urbain Le Verrier reports that a slow precession of Mercury's orbit cannot be explained by classical Newtonian mechanics. In 1915, Einstein published his work in general relativity, explaining the perihelion change in Mercury. And then in 1919, Sir Arthur Eddington performed an experiment during a total solar eclipse that confirmed Einstein's predictions. So a little bit of effects that occur during general relativity. The presence of large masses causes both space and time to curve. I'll go into a little bit of that later. This effect causes multiple perturbations to an object's orbit, including a precession in the perigee of the orbit. The rate of time lapse will also change in the presence of a massive object. Time will either slow down or increase for an observer. Emission of gravitational radiation from massive objects can lead to a decrease in an object's period, angular momentum, and energy. Even light can bend under the influence of gravity. This produces an effect called gravitational lensing. And general relativity also explains the phenomenon of a black hole. Okay, so a little bit of background on curving of space and time. So it's easy to see a two-dimensional space projected onto a three-dimensional object. It's a little bit more difficult to see a three-dimensional space projected onto a four-dimensional object, for instance, which is what is happening in general relativity. So we can see these three models below. The first one is if capital omega, critical density, is greater than 1. This means that space is closed. So what this implies is that if you were to travel in one direction in three-dimensional space, you would eventually end up at the same spot for which you started. Okay, so theory of general relativity. These are the simplest sets of equations for it. These are Einstein's field equations. Each one of the capital letters represents a tensor, which expands to a much more complicated expressions, which I won't go into. Okay, so that was a little bit of background. Now onto the orbital mechanics of general relativity itself. This first equation is the orbital differential equation, which are derived from the previous Einstein field equations. M here is the mass. U is 1 divided by the radius. H is angular momentum. And these are all in geometrized unit system, which means that mass, for instance, is in units of kilometers. That intuitively doesn't make much sense, but the way it works is just that the mass is multiplied by the gravitational constant and divided by c squared, which is the speed of light. Okay, so differentiating through and multiplying through by mass gives this equation, where capital U is m times little u, which is also m divided by r, and sigma is m over h squared. The Newtonian equation can be expressed as this third equation here. Keep in mind the only difference is that we are omitting the 3u squared term, and this equation has no general relativistic effects. And the solution to this differential equation is the solution that we should all be familiar with from Arrow 351. It is the equivalent of h squared divided by mu divided by 1 plus e cosine theta. Okay, so the Newtonian equation, like I said, leaves out the u squared term. This becomes an almost exact solution for most orbits because u is very small for these cases. For example, the sun has a mass value of only 1.475 kilometers, and Earth is revolving the sun at about 154 million kilometers, so therefore u has a value of 9.5 times e to the negative 8, and this value is also has no units associated with it. Okay, so an approximated solution for the general relativity differential equation, which was discussed earlier, it's this second equation right here, is this equation. This is not an exact solution, but it is a fairly accurate one. The third term here represents the advance of the perihelion of the orbit, so the rate of perigee change. Okay, so now we'll look at the Sun and Mercury system, and this equation right here represents the perihelion drift for one revolution, and it can be expressed as 6 pi g times the sum of the masses over speed of light squared divided by semi-major axis divided by 1 minus the eccentricity squared. And here you can see a picture of what that would look like. It's slightly exaggerated. Mercury's precession does not occur nearly that quickly. Okay, so here are orbits in highly curved spacetime. Again, our solar system is relatively flat, but this is an object orbiting a black hole. Here you can see the orbits become much more distorted. And the reason this happens is because in Einstein's theory, the inability of a particle to move at or above the speed of light creates a pit in the potential near the black hole, which I'll explain here. This orbit exists outside the Schwarzschild radius, at which point there is no escape from a black hole. You can think of the Schwarzschild radius also as the event horizon, is a more popular name for it, for a non-rotating black hole. The kinetic energy at relativistic speeds can be expressed as this equation. It's not the same as the typical kinetic energy that you would see in other physics classes of 1/2 mv squared. But if we were to take a Taylor series expansion of this equation, we could see that the first term is 1/2 mv squared. So what this ensures is that in relativistic effects, the orbit will have the same energy, but less of that energy will be represented as velocity when compared to Newtonian mechanics. Because in this orbit, the particle would have to be moving faster than the speed of light to maintain Newtonian mechanics. Okay, so here are some effects on other orbital parameters. Here you can see the energy rate dissipation and the angular momentum rate dissipation. These equations are both caused through the phenomenon of gravitational radiation, where a massive object will emit gravitational waves. And I'm not going to read out these equations. Here is the decrease in period as well. And this figure shows the decrease in an orbital period of a two-pulsar system. Keep in mind for the Mercury and Sun system, this trend will be fairly linear, but because multiple parameters are changing within here, such as the A for the semi-major axis, other parameters will change at different rates. Okay, so this is simulated parameters, orbital parameters of Mercury. And again, because the Sun is not nearly as massive as a large black hole, space-time is relatively flat, which means the trends are going to be linear. You can see angular momentum over time, 2.7 times 10 to the 9th kilometers cubed per second squared. It changes very little, as does orbital energy. Period versus time changes less than an order of seconds, and argument of perigee can be expected to change 5/1000ths of a radian over 10,000 periods. Okay, so now this is a little bit of a bonus slide, the orbit of light. The photon sphere is defined by the radius where light itself will orbit a massive body. Black holes are typically the only objects where this can be observed. This is because the orbit has to lie 3/2 times away from the object's Schwarzschild radius, and that object has to be very dense in order to satisfy that. Here you can see the equation for the photon sphere. It is 3gm over c squared. And you can see light orbiting a black hole here. Okay, so effectiveness of Newton's equations. As can be seen in the orbital perturbations of Mercury, general relativity has very minute effects on smaller objects. These perturbations will not overcome other perturbations such as J2 drag, SRP, and n-body. So for orbits that are not orbiting supermassive bodies such as black holes or neutron stars, classical Newtonian equations are a perfectly fine way of estimating orbits.